Hello, welcome back. We are beginning chapter 29, The Big Bang. This is the end with a bang, as they say, the last chapter that we'll be covering in this particular class. There is a chapter 30. It's about life in the universe. It's very interesting. You should read it, but we're not going to be covering it. We are simply ending with the biggest questions that can be asked. What were conditions like in the early universe? What is the fate of the universe? Where are we going? So that's coming up in the next class and a half. Okay, so we need to model the universe. Can we use Einstein's general relativity to model the entire universe? The answer is yes. That's one of the first tasks to which it was put. And can we use it to predict the fate of the universe? Yes, both of those questions. So let's think about the first one too. What does it mean to model the entire universe? How can we make predictions about what the universe will be like? Well, we know the universe exists. We know there's matter in the universe. We know that the matter can affect the expansion, actually. Does it slow it up or speed it down? So here's what I want you to think. How does the matter in the universe affect its expansion? Right? So what I want you to think about is what effect does matter have on other matter? It's an attractive force. The gravitational force is an attractive force. Gravity wants to pull things closer together. And so the more mass there is in the universe, or any mass in the universe, is going to act to slow that expansion down, because these space that's expanding in between these two galaxies, the galaxies actually want to be closer together. It's not quite as simple as they just want to come closer together through space. They actually physically want to stop the expansion from happening. And that's what Einstein's theory says. So we expect that the more matter there is in the universe, the faster that expansion rate is going to be slowed down. Let's take a look at this animation. Here it is. I like this animation in some respects, but I don't like it in others. So let's just say we've got a low mass density, and we begin playing our cosmic tape, and it just expands and expands and expands in a fairly linear way and doesn't really ever slow down, really. If you put more matter in the universe and begin it, you'll notice that the expansion rate's slowing down a little bit. In fact, this is very similar to, this is the average distance between galaxies, but you could imagine this as throwing an object up into the air. This one has achieved escape velocity. It's never going to come back down. But as we're not going to be throwing this thing faster and faster. We're just going to be adding more and more mass to the thing that's holding it there. The more and more mass you add to the universe, the greater the gravitational force is, the more likely it is that the universe will actually reach some large distance separation between galaxies, and then begin to contract again. Let's see if we've reached that. We have. Look what just happened there. It's sort of like, again, throwing something up into the air really fast. It moves up and up and up and up. This is like its vertical position as a function of time, reaches some maximum position, and then begins to contract a bit on itself. Well, that's weird, right? Let's try that again. Reaches some maximum. Oh, it changed the mass density on me. How dare it? Take a little bit bigger than that. Going to reach some maximum separation and then start to fall back on each other. Whoa. If we make it really big, it's going to happen. It's just going to happen a lot faster. Interesting. So this is important. The amount of mass in the universe must affect what the future history of the universe is going to be. Is it going to expand forever, or is it going to reach some maximum distance and then collapse back in on itself? And all of that should be dependent on what the density of the universe is right now. By the way, we're starting here because we know the universe is expanding and we know how fast it's expanding. So we know the slope here, but what happens next is entirely determined by how much matter there is in the actual universe itself. Okay. Let's go back to here. So it slows it down, and the more matter there is, the more likely it is that this is going to turn around and come back on itself. So let's draw some possibilities here. It's possible that we're going to define this omega, this is capital omega, the Greek omega, the density parameter. This is the ratio of the actual density in the universe to the critical density. What is the critical density? The critical density is the density the universe has that is the boundary between a universe that will expand forever and a universe that will eventually collapse back in on it. And so that sets up this to be a fairly simple and straightforward thing. Let's bring up my whiteboard, and I can show you. There's my whiteboard. So if the density universe is too high, sort of like the Goldilocks and the Three Bears version, if it's too high, then we know that this omega parameter is greater than 1. And we know that the universe will collapse back in on itself. If the universe is too low, the density parameter is too low, that is, omega is less than 1, then the universe expands forever. If it's just right, the Goldilocks universe, then omega is equal to 1, and you're exactly on the hairline trigger between those two. And it's a sort of like, again, I like the analogy with escape velocity here. This is a universe where there isn't enough mass and you're way over the escape velocity and you never come back and you have some positive velocity at distance equals infinity. This is you reach some maximum altitude and then it collapses back in itself. This is exactly the escape velocity. You slow down and slow down and slow down, but you don't reach velocity equals 0, the expansion velocity of the universe, I mean now, until you get to time equals infinity. And here, this one, at time equals infinity, you have some positive velocity still for the expansion of the universe. So that's it. Those are your 3 possibilities. You've got omega, and this omega tells you everything you need to know. If omega is 1, you live in the critical universe. If omega is greater than 1, you live in a recollapsing universe. If you live in omega less than 1, you live in a universe that's going to expand forever. Now, the cool thing about all of this, well, there's lots of cool things, but one of the cool things is, back to PowerPoint, that this density parameter also determines the shape of the universe. And again, what do I mean by shape of the universe? This is, again, a crazy thing to think about, but we're always here talking about a 2-dimensional representation of our 3-dimensional universe. And it turns out there's 3 different possibilities for what the shape of the universe could be. It could be flat, it could be closed, and it could be open. Let's talk about each one of these in turn. Whoops. Go back to the whiteboard. Here it is. So our 3 possibilities are flat. If the universe is flat, the universe is finite. Sorry, it's infinite. And the geometry is flat. I guess this looks like a flat sheet of paper. And this is the omega equals 1 case. Our critical universe gives us a geometry that is flat. And this is a universe, I'll draw the 2-dimensional, that looks just like a piece of paper, but that piece of paper extends in all directions. But there's no physical curvature within the universe itself. But it is infinite. It goes on forever in all directions. But it's like a flat sheet of paper. Okay, the next one possibility is a closed universe. Closed universe actually has a finite volume. And if you're drawing a two-dimensional representation of that, it would look like a sphere in our 3 dimensions. And this is our omega greater than 1 case. So again, if you're a two-dimensional sense, it looks kind of like a sphere. I'm messing this all up. There we go. And this is the analogy we made in the last class about an ant, a two-dimensional ant. So how can you have a finite universe? Well, this is the closed sphere here in a two-dimensional sense is a finite surface area, even though there's no center of the surface of the sphere and there's no edge to the surface of a sphere. A two-dimensional ant on the sphere could walk in one direction and eventually come back where it started from. We could live in that same kind of universe in a three-dimensional sense where we fly off in one direction and eventually come back where we started from. That's a case of a universe that doesn't have an edge, doesn't have a center, and yet has a finite volume. That could be the kind of universe we live in. Or an open universe. This is also an infinite universe, but it's saddle shaped. And this is the omega less than 1 case. I'm not going to be able to draw this. There's a decent representation on the PowerPoint slide that you can look at. Any attempt that I make here will be horrible. But all of these are 3 different directions that the universe can be curved in. In this case, you can lie this flat and it works just fine. In this case, if you try to lie this flat, you have to cut it and it won't completely fill the whole flatness. In this case, it's curved in the other direction and you'd have to fold it in order to lie it flat on a flat piece of paper. So there's not enough material here to lie it flat. There's too much material here to lie it flat. And so those are the 3 different possible geometries of the universe itself. Cool. In terms of, so you can see the saddle shape here. That's much better than I could have drawn. In terms of, again, the density parameter tells us the shape of the universe and it tells us the history of the universe. If you have the Big Bang here and you have a omega greater than 1, eventually it will recollapse into a big crunch. Omega equals omega greater than 1. This is actually a omega less than 1. Omega equals 0 will just continue expanding, coasting forever. Critical universe, omega equals 1, it will reach v equals 0, but not until t equals infinity. This is another way to visualize that. You've got an empty universe. Okay, so this is R. This is actually that RU parameter we were looking at before, say some average separation between galaxies. And this is the now parameter. And this is the different possibilities, greater than 1, equal to 1, and equal to 0. Could be any of these. Doesn't have to be equal to 1 or equal to 0. Could be any value in between these. Why are we here? What defines this as now? Well, we know the present expansion velocity of the universe, right? That is the Hubble constant. That tells us what the slope of this is. So we know where we are in terms of the slope. The question is, what did it do in the past and what is it going to do in the future? And you can see these have implications for lots of things, not only what it's going to do in the future, but what it did in the past. Look, where this reaches the 0 point is the beginning of each of these universes. Each of these different mass parameters, yes, tells us a different future of the universe, but also tells us a different past. They all started in a Big Bang, but look, this omega matter greater than 1, that's a lot less time back to the point at which that Big Bang happened, and a lot less, a little bit more here and a little bit more here. In fact, if you remember, this coasting universe, this omega matter equals 1, omega matter equals 0 universe, is what we assumed that the universe was expanding at a constant rate when we measured the age of the universe by the Hubble constant, right? We were assuming that we were on this blue line because the velocity wasn't changing. Well, we know, or at least according to this model, that any real universe has some matter in it, and that should make it so that the universe is younger than this blue line. And yet it agreed rather well. So that's a preview of what's coming up. So what is it? We add up all of the baryonic matter. We add up all of the dark matter. We don't know what it is, but we can measure it. We can tell how much is there. Let me get back to my whiteboard. We do all these things, and we can measure all of these things. And we can even break it up, right? So we've got omega total, which is the baryonic matter. That's the normal matter. Baryons are just protons and neutrons and things. So your computer and your laptop and the earth and the sun and the normal things are baryonic matter, plus the dark matter, which seems to be non-baryonic. You add these things up and you get the omega total. Great, so we can measure them. What do we get? The baryonic matter, we get 0.04, right? Okay, we need to have this add up to 1 to get to the critical universe. Great. Well, we know that's a small percentage. We know that most of it's in dark matter anyway. Great. What's dark matter? 0.23. Okay, great. Add those up, and you get 0.27, which is way less than 1. So, do we live in a coasting universe? Do we live in an open geometry universe? The answer is no, we don't. The universe, in fact, must be flat to very high order. We've measured the geometry. What would happen if the universe doesn't have a flat geometry? Well, big triangles that you draw wouldn't have angles whose sides added up to 180 degrees. Triangles that you draw, and there's lots of geometric tricks you can do to actually measure the shape of the universe, and it's extraordinarily flat. Furthermore, if it had been anything other than flat at the very beginning of the universe, if it had been a little bit open, it would have expanded to infinity very quickly. If it had been a little bit closed, it would have collapsed in on itself immediately. The fact that we are here today, 13, 14 billion years after the Big Bang, says that not only is the universe very flat today, it must have been extraordinarily flat back in the early universe. And so there's something missing. There's a piece of this puzzle that we don't have yet. We look at all the matter in the universe, it only gives us about 27% of what we know must be out there. So there's a piece of the puzzle that we don't have yet, and that will come next. Stay tuned. The mystery deepens.